All right, so let's continue with high school algebra. A little refresher. Maybe I should like pick somebody to whiteboard and solve this problem. Okay, so what is a to the power of b plus c? Okay. A to b times a to the power of c. Right? So now tell me what it is. What's the translation of this into our type algebra? Yes?
Either B, C, or A.
Aha. Okay. So this is a sum type, right? So it's like from either either B, C function to A, right? So, and this says that this is actually equivalent to a pair of functions, right? From B to A and from C to A. Yeah, does it make sense? I mean, how do you implement a function from either B, C to A? You do case analysis, right? So you really are implementing two functions, a pair of functions, right? One for left A, and left B. Why is it B? Okay, one. Left B, right? That produces an A. So it's a function from B to A. For the case left, and for case right, you need a function from C to A. Take these two functions, and you implement this function. So, miraculously, it works, huh? That's so nice. Okay, next one on my list is A to the power of B, and then again to the power of C, right? What is this? It's A to B times C, okay? So this, anybody recognizes this in type language? Currying, right? Because this is a function from C that produces a function from B to A. Okay? Well, they look like the letters are only in non-alphabetical order, but it's right. And it's the same as a function from a pair BC, right? Product pair to A. That's just currying. We are rediscovering currying. Okay, cool. Another one. A cross B to the power of C. What's that? A C cross B to the power of C, right? Okay, how does that work? So this is a function that takes a C and produces a pair AB, right? And this is a pair of functions. One function goes from C to A, and the other from C to B. Okay, does it make sense? Right? One function that produces a pair can be replaced by two functions that produce first element of the pair and the second element of the pair. Piece of cake. And anything else? Well, I guess that's good enough, right? So, huh?
Logarithms?
Logarithms. Okay, no, I don't know about logarithms here. No. But as you can see, these algebraic data types, now we can extend them to talk about functions, right? And we already know from previous lectures that just like all these products, coproducts, right, they form bifunctors. We know that the function type actually forms a profunctor, right? It's functorial in the second argument, contravariant in the first argument, right? So we have built up this whole type system from bottom up, right? Starting from category theory, from initial object, terminal object, product, coproduct, and exponential, right? We also know that this is, they form a very nice algebra, and we also know that they have all these functorial properties, that forming a product, forming an exponential, forming a coproduct has functorial or contrafunctorial properties, right? So that sort of like rounds up all this stuff. And by the way, all these algebraic things that I here kind of showed you in Haskell, really, right? They actually are true in a bicartesian closed category. You can actually do this stuff using advanced things like junctions, Yoneda theorem. But this stuff can be actually done very strictly for an arbitrary category in which these things exist. So that's very nice. Okay, so we have this impression that all these theories are very similar, right? I mean, we started with high school algebra a long time ago and operating on numbers and variables, right? Functions and so on. Now we are in programming and type theory, and we are seeing the same things in type theory. We are in category theory, we are seeing very similar things in category theory. So, like, remember what I talked in the first lecture, that like all of these things are so similar, okay? And I also mentioned that the similarity extends further. It's sort of like you have to learn just one thing and then everything else kind of falls out of it. So probably like the best thing is to start, instead of going to high school, just start with category theory, right? And then everything else will just follow from this. So the other thing that falls out from this is that exactly the same structures that we've seen here for types and for categories, they appear in logic. And that's the basis of this famous Curry-Howard isomorphism, or is sometimes called propositions as types. Okay, so that's a pretty amazing thing, that all these things that we talked about about type theory and categories, that they actually have correspondence in logic. It's like one-to-one correspondence in logic. I don't know how much. Well, we all know a little bit of logic, like you know what and or is, right? Boolean logic. That's mostly what we learn in school, right? But in general, logic is implication, stuff like this, true, false. Okay, so so this isomorphism between type theory and programming in general, lambda calculus, type theory, and logic on the other side, starts with identifying what it means to what's a proposition. Proposition in logic is a statement that can be either true or false, right? That has a truth value. So, sky is blue, okay, that's true during the day, or, maybe not in Seattle, right? But so these propositions correspond to types in programming, right? And just as a proposition can be true or false, a type can be either inhabited or not. So the truth of a proposition means that the type that corresponds to it has elements, members, right? It's inhabited. Like most of the types that we deal with are inhabited, right? But so they are kind of like true propositions. But there are also types that are not inhibited, and they correspond to false propositions. And we know one such type, that's void, right? And like everything else that's untrue is uninhibited. I always get it wrong. Okay, so these types that have no elements, right, that they are all equivalent to void type, right? So these are propositions, right? What else do we have in logic? So if we want to prove something, right, prove a proposition, we just have to show that it has an element, that the type has an element. Like if we can construct an element of the type, then we have proven the proposition, right? Okay, so there is in logic there is this there are these two basic values, true and false, right? These are propositions. True is a proposition that's always true, right? And false is the proposition that's always false, right? So the corresponding things in type theory, right, would be void type corresponds to false. Right? So maybe I should start writing like a little table. So here's logic. True corresponds to unit type. False corresponds to void type. Okay? So true corresponds to an unit type, because unit type is always inhabited. It just has one element. So it's like a canonical example of something that's inhabited, right? So that's true, that's false. Then we have conjunction, right? And takes two propositions, combines them, and it's only true when both of them are true, right? So that corresponds to a pair, so a pair, A and B. If A and B are propositions, then this pair, if A and B are types, they correspond to two propositions, A and B. We can only form a pair, right, if you give me elements of A and an element of B. That's the only way I can form a pair. Right? I need both elements. And conjunction is the same. Both of them have to be inhabited, right? Both A and B have to be inhabited for me to form a pair. Both A and B have to be true in order to form for the conjunction to be true, right? And then it goes on and on, right? A or B. Disjunction, A or B, corresponds to, well, canonically, that would be our either A or B, right? And again, in order to construct an either, I only need one element. I can just take a left or take a right. So if either is true, the disjunction is true. I don't need both of them to be true. But at least one of them has to be true, right? So either is inhabited if at least one of them is inhabited. And disjunction is true when at least one of them is true, right? Or provable. Maybe instead of saying true, so that you can prove it, right? Provable. Okay. Now this is all very, very interesting, but the most interesting part is the function type, right? So the function type corresponds to implication. That's why I was using this double arrow, right? Implication. B follows from A, right? And this is a function type. You see? If you give me an element of A, so if A is inhabited, right? If you give me an element of A, I will produce an element of B if I have a function, right? So if I have a function, then I can produce B from A, right? And same is true with implication. If A is true, then B is true. That's what it says, right? And the function eval that we used to define our function type, you know, it can be. It says that if you have a function type A arrow B, right, and you pair it or cross, let's say a cross in categorical sense. So let's do type, right? So you pair it with an element of A, right? Then you get an element of B, right? So that corresponds to what in logic is called modus ponens. If you know that B follows from A, and you know that A is true, then you can prove B, okay? So you have a proof of B if you have this, you have a function, then you have an argument, and then you can produce a result. And that's exactly what an implication is, right? So there is this beautiful one-to-one correspondence between logic and type theory. And in fact, it goes further, right? I mean, true unit, that was our terminal object, right? Terminal object. False, void. That was our initial object. Right? Pair, that was our categorical product. That was our coproduct. Right? What did I call a coproduct? Categorical. Well, let's call it this, right? And this is the function type. This is actually B to the power of A, right? So that's the exponential object, right? So we have like a three-way equivalence. That's called the Curry-Howard-Lambek isomorphism. Lambek added this third line to it, saying that in a Cartesian closed category, because you need a Cartesian closed category to be able to formulate all these things, right? Product for any two elements and exponential for any two elements, right? That a Cartesian closed category is a model for logic and it's a model for type theory. So all these three things are the same. And what people do is usually mathematicians are the first to discover some new logic. So it usually goes like this, you know, mathematicians come up with some new way of doing logic, like linear logic, for instance, and then computer scientists pick it up and say, okay, so if we translate linear logic using Curry-Howard isomorphism, what kind of type system do we get, right? We get linear types, right? Have you heard of linear types? No? This is like, well, in C++ you have these unique pointers, right? That stuff is moved from one place to another and you cannot use it twice, you can only use it once and you destroy it, right? So linear types. What is the language that recently started using linear types? Is it Rust?
Rust uses a affine type. So
yeah.
These ones.
Okay. Well, so linear types are useful. There are some logics that correspond to concurrency, for instance, and so on. So there is cross-pollination between these different areas, between type theory, lambda calculus, logic. So I think maybe this will be a shorter lecture because I don't want to start natural transformations at this point in the middle of the lecture. So we'll postpone natural transformations to the next one, okay? And that will be it for today. Okay, thank you.